Hi guys, welcome to today's tutorial. We're working on worksheet number 10 about some optimization problems. Today let's take a look at question number 2. Copy and paste here. We have a ellipse and then we need to inscript a rectangle inside it. We want the rectangle to have the largest area. So let's graph the diagram first. Ellipse. It looks like this. That's ugly. Try again. Okay, better. Right. And then the rectangle looks like this. Okay, something like that. Okay, and then so this is the length of the rectangle, right? So if we assume that this is x, if this is x here, then the length will be 2x, right? Because this part and this part, they're exactly the same. So this is also x, right? So both of these together, that is both of these together, that is 2x. Okay, both of these together. Okay, and then if we assume that this is y, then y here, then the height will be 2y, right? And then by our setting here, then the coordinate of this point will just become x comma y, right? So we want to kind of move this point so that we can change the shape of this rectangle, and then at some point that this rectangle will have the largest area. Just imagine this: if I move this point kind of to here, then I can change the shape of this triangle. For example, if the point is here, right? So the triangle becomes more skinny, right? Like this. If I move this point down here, right, then this triangle, this rectangle becomes more flat, right? So there must be a point such that the triangle has the largest area, right? So the first step to do after we finish this setup is to write out the area expression of the rectangle, right? We know that the area of the rectangle is the length of the side times the height, right? So that is a equal to 2x times 2y, which is equal to 4xy. Right? And we also know that we can only have one variable, so we need to eliminate one of these two variables, either x or y, right? Like how we do the questions for the related race questions. We eliminate one of the variables by using some kind of relations. So the relation that we have is this. That is the equation of the ellipse, right? So if you manipulate the terms here, you can use maybe the variable y to represent the variable x. So let's see how we do that. If we move this x term, for example, to the other side, right? So we have y squared over b squared equal to 1 minus x squared over a squared, right? And then we can take the square root, right? Knowing that both y and b are positive, right? So we can take the square root. In this case, y over b equal to, y over b of this one equal to square root of 1 minus x squared over a squared, which gives you that this is equal to y over b, right? So it gives you y over b equal to this one again. And then you kind of multiply b on both sides. B here, so this b cancel with this b, so you have y equal to b times this 1 minus, right? And after this you can substitute this back into the expression we've just obtained to get rid of the variable y, so you only have one variable here. And then now you have created your function a of x, right, is equal to 4x times this b, right, times this 1 minus x squared or b squared, right? And then we simplify this a little bit, so it becomes, oh, this is a, not b, this one here. So it becomes this 4bx, right, times this 1 over 1 minus x squared over this, and we can change the thing inside the underneath the square root, so it becomes a squared minus x squared over a squared, right? And then we can just take the square root for the numerator and the denominator separately, right? And we know that a is greater than 0, so this simplifies to a squared minus x squared over a. Okay, so that looks much better. So this is our function, and then we are gonna apply those derivative stuff to get the max and min. But before we do that, we need to figure out the domain of this function, right? So the domain of this function, of course, depends on the setup here. So as you move this point, you can see that you can only move this point on the first quadrant, so that is the arc here, right? So we can assume that x, it's from 0 to a, right? Actually, you can assume x is a negative number, but that does not help us. If you move this point across this y-axis to the other side, then you're just essentially mirroring this rectangle to the other side. So it gives you the same kind of stuff, right? So it is unnecessary to assume x to be a negative value. So only considering x in this interval will give us the answer. So that is why we can just assume that x is from 0 to a closed interval. Some of you may ask, why don't we use open interval? because if x is 0, then the area of the triangle, the area of the rectangle will just become 0. That is not meaningful, right? But if we use open interval, then we will have more difficulty to figure out the min and max later on, because it's easier to do it on closed interval since we have the closed interval method, and that is one of the reasons we prefer closed interval instead of open interval. Okay, so assume that x is this thing here, that is our domain, right? And after this, we're gonna take the derivative of this function, right, and find out the critical numbers. So we know the max is obtained either on the endpoints or on the critical numbers, right? So take the derivative, and we're using of course, the product rule here. Firstly, knowing that this 4a over b is just the coefficient, so we can ignore it, just factor it out here, right? Not doing anything to it. And the function we are taking the derivative of is actually the x times the square root of a squared minus x squared. So that is use the product rule, right? So it's the derivative of x, which is 1, times the other function, and plus x times the derivative of the other function, which we apply the chain rule here, and we can think of this as this guy here as a squared minus x squared to the 1 over 2, and apply the product rule. The power rule. So that is 1 over 2, right, times is a squared minus x squared to the negative 1 over 2, right, and apply the chain rule times negative 2x. Okay, and simplify this a little bit, right? This 2 cancel with this 2, right? And then we have 4b over a. This is minus x squared plus, and there we have a negative sign, so actually this turns into a negative sign, right? I mean, the negative sign is here, right? There's a negative sign. So we have x squared, right, times this 1 over, this negative 1 over 2, and the exponent turns into the square root in the denominator. Okay, like this. And the next step, we want to factor out this guy, right, so that we have a nice form inside the bracket. So factor this out. 1 over is a squared minus x squared. Right. So factor this out. That means we need to divide every term inside this bracket by this fraction. And we know dividing a fraction is actually equivalent to multiplying its reciprocal, right? So this term here turns into just a squared minus x squared, right? Since you are dividing this by 1 over this square root. Okay, so that is minus x squared. This is square bracket, and then simplify it further. So we have a squared minus 2x squared, right? Since we have this thing in the denominator, so we know that this can be 0, right? So if x is equal to a, then this is undefined, right? And therefore, the critical numbers must include x equal to a, right? So critical numbers x equal to a, right? Some people may say, oh, when x is equal to negative a, then this denominator is also 0. But keep in mind that x equal to negative a is not inside our domain. Our domain is x from 0 to a, right? So we only consider those numbers inside our domain, right? When x is equal to a, this derivative does not exist, so a is a critical number. And also we need to consider where the derivative is equal to 0, right? It's when this bracket equal to 0, since the green stuff here, the green circle here, cannot be 0, right? So the only possibility for the derivative to be 0 is when that bracket equal to 0. That means this guy equal to 0. And you solve this, you can find out that 2x squared is equal to a squared, right? So x squared is equal to a squared divided by 2, and take the square root, right? X is positive, so we have this a over square root of 2, right? So this guy is the other critical number, x equal to, right? And I have mentioned that we just need to plug in the critical numbers as well as the endpoints into the original function and see what the greatest value is. The greatest value is the greatest area. Okay, and since x equal to a is just is already the endpoint, so we just need to test, find out a0. A over square root of 2 and a, right? Find these three things. So let us remind us what the original function is. The original function is this guy here. Right? So a0 is equal to, you plug in 0, right? So we have 0 here, right? Because this x is here, right? If you plug in 0, you have 0. And you plug in x equal to a over square root of 2. So you have this 4b times a over square root of 2, right, times there's a squared minus a over square root of 2 bracket square over this a, right? This a cancel with this a, right? And then you can find out the thing underneath square root, that is a squared over 2, right? And then take the square root, that becomes just 4b over square root of 2 times this a over square root of 2, right? So it becomes just 2 times, square root of 2 times square root of 2 is 2, right? And then this cancel with the 4, so we have 2 on the top left. So the final answer is 2ab, right? So this guy is equal to 2ab. Okay, 2ab. And we also need to plug in x equal to a. And you see that if you plug in x equal to a, this guy here is 0, right? So a is also 0. And since we know that a and b are both positive numbers, so it's obvious that the function a of x obtains the maximum value at the place x equal to a over square root of 2. So this is our maximum value. Right? So now we can draw our conclusion that hence the largest area is 2ab when x equal to a over square root of 2, right? And we also need to find what y is in this case, since we need to find the dimension of this rectangle. So y is equal to what? Y is equal to this thing here, right? So we just need to substitute x equal to square root of 2, maybe just copy and paste into so in this case, this y is equal to b times 1 minus this a square, a over square root of 2 square over a square, right? That is b times this 1 minus a square over 2, right, divided by a square, so cancel a square here, right? And that is b times square root of 1 minus 1 over 2. So this is, just b over square root of 2 if you compute this. So y is equal to b square root of 2. That is our conclusion. So what does that mean? You can imagine if you go back to the picture, it is like a is around here. I mean, going back to the picture. This is our a, right? So we want x equal to a divided by square root of 2. So approximately here, in this place, the rectangle will have the largest area, right? And it looks like it's true, right? This rectangle, it looks like this rectangle has a larger area than the previous rectangle. So that is what it means in our original diagram. So let's summarize for this question. We firstly draw our diagram to find out how we can inscript a rectangle inside this ellipse. We can set up a point on the first quadrant on the curve, right? And then we can move this point freely, and for each of this point we can form a rectangle. So when this point changes, the area of this rectangle also changes, right? So we want to find a point that makes the maximum rectangle. So we write out the expression of the area of the rectangle, a of x, right? And then we have two variables here, so we need to eliminate one of them by using the given expression. And after we do that, this expression is written in terms of only x, right? And then we also need a domain of this function. And then we take the derivative, and we went through some of the complicated computation, but we finally got to the end. That is not easy. And we find the critical numbers by considering where the derivative does not exist and where the derivative is equal to 0. And since we are using closed interval methods, we plug in all those critical numbers as well as the endpoints into the original function and see what those outputs are. And then we compare the values among all the outputs and see that the maximum value is obtained here. Okay, so that's it for this question. So that's it for today. If you like my videos, make sure to subscribe to my channel. I'll make more videos about that in the future. So see you guys in the next episode.